Hi there. So today I want to introduce the concepts of self-assembly and also discuss heteroepitaxy. So what is self-assembly? Well, if you're thinking like a typical moviegoer, you might be picturing something from Big Hero 6, where you have all these little mini robots that can assemble into a gigantic man-eating killing machine robot. And maybe that's not a bad place to start from our definition of self-assembly, more commonly used by nanotechnologists. So nanotechnologists use a technique called self-assembly to build structures using nanoparticles, or to build nanoparticles using molecules. Self-assembly involves creating conditions so that atoms and molecules arrange themselves in a specific way to create a material. And of course, this is a form of the bottom-up approach in fabrication of nanostructures. And the spontaneous organization can be due to direct specific interaction or indirectly through the environment. So today I want to discuss heteroepitaxy as a form of self-assembly specifically for structures like quantum dots. So if you remember, we talked about epitaxy, or specifically molecular beam epitaxy, in a different lecture. Epitaxy refers to the deposition of a crystalline overlayer on a crystalline substrate, so it's solid on solid. The term epitaxy comes from the Greek root epi, which means above, and taxis, which means an ordered manner, and it can be translated as arranging upon. Epitaxial films can be grown from gaseous or liquid precursors. Because the substrate acts as a seed crystal, the film that gets deposited in the overlayer may lock into one or more crystallographic orientations with respect to the substrate crystal. If the epitaxial film is deposited on a substrate of the same composition, it's called homoepitaxy. It's also called not extremely interesting most of the time. But otherwise, it's called heteroepitaxy, which is what we're going to deal with today. Now, back to the idea that the substrate acts as the seed crystal and the deposited film locks into that crystallographic orientation. That's kind of shown here on the side, and it sort of makes sense if you just think about having, for example, a box full of little ping pong balls or something like that. And then you drop balls of different sizes into the box of the ping pong balls, and it forms that solid surface, right? So then you have your new balls coming in, and it's going to drop into the divots already established by your ping pong balls. Okay, so you can kind of think of it that way. You've got a potential surface, a potential well, a series of potential wells associated with the surface, and the new atoms that you put down are going to kind of lock into the wells. And that's why you sort of have the crystallographic mimicry for the add layer, the add atoms on that substrate. So, like I said, heteroepitaxy is used in one way to grow quantum dots. It's got other applications, of course, but quantum dots are of great interest to us in our nanoscience class. So, heteroepitaxy is often used to grow these quantum dots and other structures that are important to nanoscience, and that's why we're talking about them today. So, here in the picture, you can see this is a scanning probe microscopy image of some quantum dots deposited on a substrate. And you can see they have kind of a random growth pattern over here, or it can be locked into growing in a very regular array depending on what you do with your surface and how you treat it and your conditions. So steps in heteroepitaxy, how does it work? Well, you have your initial nucleation stage where you have atoms or molecules that are brought to the surface. And then once they're on the surface, they adsorb or diffuse, they move around, they stick to the surface, that's adsorb, and they diffuse, move around on that surface until they join or nucleate with another add atom. And eventually they form little islands. Or if you're putting it down, they may attach to an existing island, or it can come down, it can stick for a second, and then it can desorb and fly away, okay? Now, once the little islands begin to form, you have an aggregation stage where small islands grow, migrate, or evaporate. And then at some critical size, they kind of become stable. And then you have a coalescence stage where existing islands are growing so large that they then begin to grow outward and merge with other large clusters. All right? Now, so that you get a feel for what heteroepitaxy is like, I have a series of movies that are required for you to watch posted underneath this online lecture. So we've got a low energy electron microscopy movie of atomic layer by layer growth of cobalt on ruthenium by molecular beam epitaxy. Okay, so that's one of the movies I want you to see. And then also there's a Monte Carlo simulation of the main processes that happen in MBE. And then finally an STM movie of gold film growth. So I want you to watch all those so you can kind of get a feel for what molecular beam epitaxy is like. But now on to the physics. So when you deposit one solid surface on top of another solid surface, there's three different possibilities of what might happen. We're going to talk about the one where there's no real mixing of the materials, and we're only going to discuss epitaxial growth. But it's important to realize that there could be other options. You could have diffusion if one solid is soluble in the other, and then you'd have your A material up here, your B material down here, and then sort of this mid-region, which is a mix or an alloy, if you will, of the two materials. You could also have a boundary layer if A and B are chemically reactive. So you have A sitting on B, it then reacts with B, forms a kind of reactive compound, a new compound in that mid-layer region, and then A forms on top as you continue to grow the film outward. So we're not going to discuss B and C here. We're just going to discuss when you deposit A on top of B, and they pretty much stay that way, A on top of B. No diffusion, no chemical reaction. Now, when you do this, when you put a new material on top of a different material, you're going to have some strain in the lattice. Now, if you need a review of the concepts of strain and stress, then I have posted a lecture, an online lecture that I prepared for material science class along with this one. So you can go back and review those concepts. Now, structural differences can cause strain, like if you try to put a face-centered cubic film on top of a hexagonal closed-packed substrate. So if the films themselves want to have a different crystalline structure, for example, if you have, something like graphite and you're putting something like iron or something on top of it, I mean, that's crazy, but whatever, then that's going to cause strain because they don't want to pack the same way. You have different coefficients of thermal expansion that can cause temperature-dependent strain. Okay. If you have relative bonding energies of adsorbate and absorbate or adsorbate to substrate, then that can cause strain. And there's a lot of other reasons that can cause strain too. This is still an area of research. There's papers being published probably just this week on simulations of MBE or new ways to deposit, new techniques, new treatments. So let's define strain mathematically. We're going to deal with a type of strain that's caused in differences in the lattice spacing. This is called misfit strain. And so what that is let's define it mathematically as epsilon naught is equal to AL minus AS divided by AS. And here AL is the spacing of the overlayer's lattice, and then AS is the spacing of the substrate lattice. Now this number could be expressed in a decimal form like 0.02, or you could multiply the 0.02 times 100% and say 2%. Okay, both are done in this lecture, so it's done kind of back and forth. Now the strain could be anisotropic. It doesn't have to be the same in all directions if you don't have a cubic lattice. If you do have a cubic lattice, it is an isotropic strain. Strain's a deformation of the lattice, and that deformation leads to stress in the film. And on a two-dimensional surface, if you're depositing, a single layer of film and you're not talking about bulk stress and strain, then surface stress is force per unit length, not force per unit area. So when you make the transition from material A to material B, the composition has to change from pure A to pure B within just a few atomic layers. The structure, on the other hand, changes from the structure of pure A to the structure of pure B over a much longer length scale. And this is frequently the case for materials of similar structure but with different lattice constants. The long-range change of structure allows for a gradual easing of the strain associated with the formation of an interface between the two materials with lattices that don't exactly match. That's pictured over here in cartoon format. You can see here that your substrate has a particular spacing. Then when you put down the first layer of film, it mimics that spacing. But as you add layers onto it, it'll gradually relax into the spacing that it would have in the bulk if it were on its own. Okay? Now, we have a supplemental textbook. Let me mention that. I'm going to post a link to that on our course website. But you can also just access it through App State's library. It's called Surface Science, and it's written by a guy named Kolsinski. Okay, so I'm referencing his equations in here. It's free and online, though, so you should access that reference. Now he defines the elastic strain energy per unit area this way: 1/2 Hm epsilon naught squared. And here H is the film thickness, and M is the modulus for the biaxial strain, which is sort of a 2D equivalent of a Young's modulus. Again, if you need a review of Young's modulus, there's another lecture posted on the course website on stress and strain. Now, note that the strain energy increases as the thickness of the layer increases. And because, of course, it makes sense, there's no strain if your thickness approaches zero. If you've not got a film, you've not got any strain. Now, one mechanism of strain relief in thicker films is the introduction of defects, or misfit dislocations, in the interface. This generally only occurs after the overlayer has grown to a value greater than the critical thickness. And of course, that's because, in the first layer, it's just going to mimic the substrate spacing anyway. Alternatively, the upper layer of the overlayer can experience roughening to relax the interfacial strain. Okay, so instead of a nice uniform film, it forms kind of island growth. These mechanisms of strain relief, along with interdiffusion, where you have material A kind of moving into material B, can appear either cooperatively or competitively. Okay, so you can see here the misfit dislocations in this little cartoon are represented by the circles with white inside there. And they only form once that overlayer has reached their critical thickness. You can see these things coming in further up the film. And this is the thickness beyond which the fully strained layers is no longer stable. And this was first defined by Frank and Vandermeer. Now, the equation that describes this critical thickness, it's really a proportionality, more of an equation. H sub c here is the critical thickness, and it's proportional to 1 over epsilon naught, or the strain. And that makes sense because as the strain goes to 0, then that critical thickness would approach infinity. In other words, if it's homoepitaxy and you're plotting exactly the same thing, then you wouldn't need to relieve strain. So if you have a liquid film forming on top of a solid substrate, then there's no crystalline structure, and so there's no directional dependence on a surface tension or surface energy, and so the surface energy equals the surface tension. This isn't the case for solids. Crystalline materials are going to spontaneously form particles of particular shapes that reflect the symmetry of their lattice and expose the surfaces which exhibit the lowest surface energies. Because remember, as we discussed, you could have different crystalline faces in a solid material, and because of the way those things are packed, their different crystalline faces are going to have different surface energies. So cubic materials, for example, they form cubic crystallites, whereas hexagonal materials have a tendency to pack themselves into crystallites with angled faces. Okay. Now here you see an example of that. This is an image, an AFM image, showing the growth of a crystal on top of a substrate, and you can see that it tends to form these little rectangles on top of the surface. Okay, and that's just because that's the crystalline structure of that material in the bulk. Now, investigations of solid-on-solid growth reveal basically 3 different types of growth modes. And the appearance of strain, resulting mainly from lattice mismatch, is the biggest reason why you have these different growth modes. Now, in slides to come, I'm going to use theta to symbolize the film thickness in monolayers. So H is the film thickness, say, in units of distance, and theta is a dimensionless, just the number of layers that have grown up. So, okay, so get ready for that. Now, the 3 different types of growth modes that I'm going to discuss are Vandermeer growth, Stransky-Krasnoff growth, and Vollmer-Weber growth. Now, those are kind of mouthfuls, so I might use acronyms like VM, SK, and VW to refer to them here on out. Okay, so Vollmer-Weber, or VW, growth mode. The growth of the epitaxial thin film on a single crystal surface depends critically on the interaction strength between those atoms which are coming in towards the surface and the substrate atoms at the surface. Now, while it's possible to grow epilayers from a liquid solution, most epitaxial growth that we're going to discuss here is done by MBE, or molecular beam epitaxy. In VW growth, add-atom interactions are stronger than those of add-atom surface atom interactions, and that leads to the formation of 3-dimensional add-atom clusters, or islands, okay, as pictured in column C here, all right? And the growth of these clusters, along with coarsening, causes these rough multi-layer films to grow on the substrate surface. So in other words, it doesn't form in VW growth these type of flat surface films, okay? It forms these islands, and the islands get taller and taller, and that leads to a rough surface. Now, as opposed to that, in Frank Vandermeer growth, atoms have balanced interaction with surface atoms. They attach preferentially to surface sites, and that results in atomically smooth, fully formed layers. And this layer-by-layer growth is 2-dimensional, indicating that complete films form prior to the growth of any subsequent layers. So here in column A, that's Frank Vandermeer layer by layer growth. Okay, these nice, beautiful, flat layers form as the films grow epitaxially. Now, SK growth is an intermediary process, and it has both 2D layer and 3D island growth. The transition from the layer by layer to island-based growth occurs at a critical layer thickness, which is highly dependent on the chemical and physical properties, such as surface energies and lattice parameters of the substrate and film. Okay, so here in SK growth, you can see films form, and then on top of those films, islands grow, or alternatively, sometimes islands grow and then films form, but it's a mix. Now, you can summarize the conditions for the three growth modes as dependent upon their strain and their add-atom substrate interactions as follows. For Vandermeer growth, your strain is usually less than 1.5% or so, and there's balanced interactions, which leads to that layer-by-layer growth. Okay, so in other words, the crystalline spacing of the substrate and the overlayer match pretty well, and they like to interact with one another. Okay. Now, for Vollmer-Weber growth, however, the adsorbate likes to stick to each other much better than the adsorbate likes to stick to the substrate, okay? And that's coupled with a lattice mismatch. And that is too great to be relieved by any subtle structural relaxations, and so you just get the formation of these big islands that leads to a rough surface. In SK growth, you have a pretty decent lattice mismatch, 2% or so. And then after the growth of the wetting layer, often which is 1 to 4 layers thick, the overlayer can't continue to grow in the strain. It's just too much, and it starts to relax and form these islands. Okay. Now, SK growth is the most commonly observed growth mode. It's also an intriguing growth mode because it's sometimes accompanied by the observations of islands with a small size distribution. It has an optimum size, in other words, and then those islands form ordered arrays. The spontaneous formation of these islands represents a type of self-assembly process that is often used for quantum dot fabrication and formation. The interplay between the kinetics and the thermodynamics in determining the shape and size of the islands remains a topic of intense study. Island formation in semiconductor epitaxy, like silicon-germanium systems, has attracted a lot of interest because of the unique optical and electronic properties of the semiconductor quantum dots. Quantum dots, if you remember from a previous lecture, get their name from the observation of size-dependent quantum mechanical effects in these nanoscale objects. So in other words, quantum dots are basically semiconductors in small nanoparticle size. Okay, so here's an example from the literature of an SK growth. So this is the deposition of germanium on top of a silicon 100 surface. And it forms a wetting layer film of about 3 monolayers thick, coating this silicon substrate, and then the germanium islands begin to form. And they're dislocation-free and they're coherent. So you get different shapes, both square shapes, pyramidal, and dome-shaped islands are formed, and the evolution of those islands has been investigated by a group of scientists cited here during CVD growth of germanium on silicon. So here's some interesting pictures of those growth modes. And here's some more SEM pictures of their growth. So you can see here, it starts out, there's the pyramid form, and you can see how that looks in the SEM. And then it goes in sort of a transition region, and then it forms the domes. Okay. Now, there's been some work done to calculate the phase diagram of this system. And here in this plot, they plot H for coverage versus lattice mismatch in fractional or decimal form. And the phase diagram confirms that Stransky-Kraskanov, SK growth, Vollmer-Weber growth, and Frank Vandermeer growth can each represent the equilibrium growth mode for an appropriate combination of deposited material and lattice mismatch. So here, 2 SK phases are found, differing as to whether the wetting layer forms before or after the islands form. And then there's also these ripening phases, designated R1, R2, and R3. And ripening here, if you remember, means what sizes of islands form or how they coalesce into larger islands, like the Ostwald ripening that we discussed in previous lectures. Okay, so you can see here you get different growth modes depending on what the strain is, what the coverage is, and how you treat the film. So in summary, By carefully controlling the parameters of the films, including the temperature, the pressure at which the MBE is conducted, adding surfactant layers to the surface, etc., scientists can control the types of films or structures that are grown. And this, if you set the conditions up right and then perform your MBE, this is a form of self-assembly, as the conditions are set by the experiment and then the structures spontaneously form once those conditions are set. Okay, so I hope you enjoyed that, and if you have any questions about the material, please do let me know.